Okay, let's start. So, morning everyone. I hope you have a good week. So, we've been talking about the greedy algorithms, the iterative algorithms in milestone 4 and how to optimize your solution. I've been drawing these paths to explain the different perturbations we can make, but that's probably not what you want to do during your program because that's a bit slow, obviously, and like you cannot probably draw every single combination of your delivery order. So how do we represent the solution in the algorithm such that it keeps running as fast as possible? Okay, so one option is to use the exact data structure that is given to you in M4, which is you're supposed to return, which contains all of the intermediate solutions. So you are given this courier subpath class, and inside it you define an intersection ID for the start intersection, an intersection ID for the end intersection, and the subpath between them. And because we have multiple derivatives, you're probably going to return a vector of these subpaths. So let's say this is one courier subpath. It starts at intersection 53, it ends at intersection 28, and between them we draw the subpath which is taken from whatever pathfinding algorithm that you're using, probably from milestone 3. Okay? So here is an example. So we have 3 depots here and for 3 deliveries. So we say that we're going from depot 0 to the first delivery, pick it up, drop it off, etc. And each color of these is basically a different courier subpath. And we're going to return a vector of these to represent the whole traveling path for the courier delivery service. Okay, so what do you think? Is this a good idea to use in your algorithm, like while you're doing a lot of perturbations in milestone 4? Like in milestone 4, all we care about is doing perturbations on the delivery order such that we can minimize the overall travel time, right? So is this a good data structure to use? It's totally feasible to use. I'm just asking like whether you think it's, yes, go. Yes. So one thing is that it probably will slow you down because there are a lot of copies of these paths that you are trying to copy from whatever algorithm that you're using to find the path between 2 intersections to these courier subpaths. So while doing a lot of perturbations, you're going to keep copying from that algorithm, and that definitely will slow you down. Okay? So all we care about here is to do faster improvement, faster perturbations on the solution. And at the end, once we find a good enough solution, we can basically construct this data structure and return it to the user. Okay? So it has basically more info than what we need. All we care about is to perturb the order of those deliveries. So better for optimization, we want to turn this data structure that you're using into only what we need for this algorithm, right? So again, let's draw the solution here again. And one way to do this is to, for example, let's define this small data structure called pickup or drop-off, which only identifies an intersection, whether it's a pickup or a drop-off, and the intersection ID. Okay? So if we construct a vector of these pickup or drop-offs, we can just say that by looking at it, we can know that this is the delivery order that we're going to take. So we're going to pick up delivery 0. Okay? We're going to drop off delivery 0, and then pick up 1, pick up 3, drop off 3, drop off 1, pick up 2, drop off 2. Okay? And in these ones, basically, I'm not showing them here, but inside that data structure, small data structure, you're just going to store the intersection ID because this is what you want. And you can actually query it from the list of deliveries that you're given in the problem anyway. Okay. What about the depots? You can also define a new data structure called pickup, drop-off, or depot, for example, and that identifies a depot intersection as well. And you can add it to your vector of delivery orders, right? So here it's clear that we are starting at depot 0 and ending at depot 2. When we do the perturbations, all we care about is doing perturbations on this vector. Now, if I'm using this representation, whatever it is, whether with depots or not, we probably need two functions, right? One function that can quickly evaluate the overall travel time of this delivery order, and that relies on the big data structure or the big matrix that we constructed in the previous lecture, which gives us the best travel time from any intersection of interest to any other intersection of interest, right? So we built that one to quickly evaluate these paths, and here we can do the same. So you'll write a function that takes in a vector of such a representation, and it will quickly return the overall travel time or the overall cost of your solution. The other function that you probably need to write is a function that takes in a delivery order such as this, and it will return a Boolean variable telling you whether this is a legal solution or not. Because remember, when we do a lot of these perturbations, some of the solutions that you can generate are more likely to be illegal, and you probably need to throw them away or try to legalize them somehow. So yeah, you would need at least two functions on top of these, on top of this representation. Okay. One thing I forgot to mention is that in this milestone, there is no constraint on the depots, right? You can start at any depot and end up at any depot, right? So it might be easier. I think I mentioned this last week. Last lecture is that you don't have to store the repos, right? You can just store the delivery order, try to optimize that delivery order. At the end of the solution, you can just find the closest delivery to the starting, the closest depot to the starting delivery, and you can connect that, and the closest one to the end delivery. Yes?
But couldn't the time it takes to go from the start depot to your first point and the last point to your end depot, couldn't that impact what is the fastest path?
Yes, but it's kind of a greedy solution because you only have these many depots, right? Like there is no other solution around it. If you optimize the overall travel path of the courier itself, like the schedule of the deliveries, okay, then you're guaranteeing, you probably can find a better solution, but I really doubt it. Then you're guaranteeing that if you choose the closest depot to the start and closest depot to the end, this is the minimum travel time you're gonna get, right? It's more likely than not, this is the best that you can do, even if you include the depot in your solution. Now, if you include the depot in your representation, it will probably be more difficult to legalize or find legal solutions, because when you swap deliveries, you're also swapping, for example, these depots as well. And like if you swap a depot to the middle, you'll probably throw away that solution or try to legalize it, which will take you more CPU time from you, right?
So it just might work out in the end.
Yes. So, yes, this is the one. Yeah, no problem. Okay, so we looked at this representation. Now let's take a look at some of the heuristics that we discussed in the previous lectures and how to work on such a delivery order. So let's say we are given this path. Again, I'm only drawing it here for illustration, but in your solution you probably won't be drawing it. Okay, and let's look at the delivery order here. So if you look at here, we are saying that we're going to pick up 1 first and then pick up 3, and this is what it's showing here. Now, I'm not showing the depots as well, but like let's say we chose the closest depot to the start. So we picked up 1, picked up 3, and then we pick up 2. You keep following that delivery, that order, and this is your overall path. Now, again, let's say we wrote a function that would evaluate this delivery order and return the overall travel time. In this case, travel time is 81. Okay, so let's look at the first heuristic that we can do, the first perturbation operator that we can do. So the easiest one is to just move one pickup or drop off either earlier in the order or later in the order. Okay, so let's say that, what did I do here? So we kept 1, we kept 3, we kept 2. Okay, we took the drop off of 1 and we shifted it to the end. That's all what we did here. So now you can try all combinations in your algorithm if you have enough CPU time, or you can just choose randomly, like say, from C++, there are a lot of random number generator libraries. You can say that I'm gonna take a random number, take a random index of the delivery from the delivery order, and I'm gonna choose another random delivery index where I want to place that delivery order and just move it there. In this case, I'm trying to move 1 to the end of this delivery order. Okay, so this would translate to a new drawing now. So because we are not going from 2 to 1 to 3 anymore, we will remove these 2 edges. Okay, and now we keep following. So once we reach 2, we are saying that we're going to go to drop of 3. So this is the new edge. And then at the end, it keeps going the same way because we are just shifting. At the end, we're just going to go from dropping off 2 to dropping off 1. Now, because we are not storing the depots in the solution, it is easier to just take that new solution and connect the new depot. Because if you look at it here now, it's illegal. So to just legalize it, take that end intersection, a new end intersection, and connect it to the closest depot it can connect to. Okay, we call the function that evaluates the overall travel time, and we find that the total travel time is now 99. So this is a worst solution. We're saying don't take it. Okay, so when you do a lot of these combinations, a lot of these perturbations, especially if your solution is well optimized, more likely than not, you will end up with a solution that is worse. But that's fine. This is the good thing about iterative improvements. You're just trying to do as many perturbations as possible as long as you have enough CPU time to try different things. If you find a better solution, that's good. You ended up like, you were lucky. If not, throw it away and try again. And if you're using random numbers, you probably like end up trying different combinations anyway. Okay. So let's go back to the original solution. We revert to because it's better, and we will keep that one. Okay. Let's look at another perturbation operator that we talked about, which is swapping 2 intersections or 2 deliveries. So again, you can try all of the combinations in the vector. You can choose any 2 deliveries to swap, and that's an order of n choose 2. If you have enough CPU time, that's fine, do it. If not, then just choose any 2 random indices in the vector and try to swap them. Okay, so let's say that I chose to swap dropping off 0 and dropping off 2. So dropping off 0 and dropping off 2 turned out to be at the end of my delivery order. I'm just gonna, because I'm swapping these, I need to remove this big edge and connect it from 0 to 2, and then I'll probably have to reverse 2 to 0. Okay, so we did we just swapped 2 intersections, and that resulted in removing these 2 edges, removing one edge and reversing the other. Okay, so we legalized by connecting to the closest depot, and that's my new solution. Okay, so your new solution is the same vector, except that the last 2 indices are swapped. And my total travel time here turned out to be 72, which is good. Okay, this is a better solution than the previous one, and I'm gonna take it and continue to improve on it by doing more perturbations. Okay, so the third operator that we talked about in the previous lecture, which is a more powerful one, it's called 2opt. And remember, 2opt basically cuts your delivery order into 3 pieces and try to connect them in a different way. And because we have this vector of delivery order representation, it's very easy to do so. Again, remember there are around 1 million combinations to do this 2opt. You're free to try all of them, but let's say I randomly chose 2 where I want to cut my vector. So I say that I'm gonna delete these 2 connections, and when we decide where to delete, you can assume that we're just drawing bars around the different pieces. So let's say I'm gonna cut the edge from 1 to 3, and I'm gonna cut the edge from dropping off 1 to dropping off 3. Okay, so now I'm left with 3 pieces. One piece that connects only picking up 1. The other piece is picking up 3 and 2 and dropping off 1, and the third piece is this big one. Okay, and that translates to basically cutting these 2 edges if you see them here, right? So we have 3 pieces. Okay, so what can you do with 2ops? With 2ops, there are several ways to reconnect your different pieces. One of them is to reverse any of these pieces. The other one is to change the order of these pieces. Okay, so you can move this whole piece to be in the second position, Or you can just keep it as is and reverse one of these pieces. You can reverse 3 to 1 to be 1 to 3, for example. Okay? So what did I do here? I decided to keep one as is, the first piece, and reverse the rest. Because now, if you look at it here, it's illegal. I have to reverse it. So I reversed the 3 to 1 to 3 to 1 to 3, and this is my new delivery order. Oops. Yeah. Okay. So in general, with any 2 up perturbation, there are 3 steps that you can follow. 1, pick the order of the 3 sub-S, okay, or the 3 pieces that you want to control. Now you can keep them as is. You can modify the order in any way or shape you want. 2, reverse any or all of the sub-pass. You can reverse all of them as well. It's one of the combinations that you can try. And 3, check if it's legal. Now, if you significantly perturb the order, more likely you will end up with an illegal solution that you either have to legalize or throw it away and try a new perturbation, right? But again, that's a good thing about iterative improvements. You can just try different things and see what works. Any questions on this? Okay. So, yeah, this is about like the representation of the solution during the algorithm that I want to talk about. And now let's talk more about heuristics in general and what we've learned so far and what we can do better. Again, this is an open-ended milestone that you can choose to implement any way you want. We talked a little bit about some of the heuristics that work well, but you can definitely come up with your own solution and see what works. Okay. So in general, when we talk about computationally hard problems, we usually try to look at what is the shape of the the solution, right? Now, the hardest problem that you are given has around 200 deliveries. So if we assume one dimension for each delivery, that's a 200-dimensional search space that you're looking into. Obviously, we cannot visualize such a search space, and it's probably very hard to traverse. So for ease of explanation, I'm just going to try to project all of these 200 into one dimension, which is called the solution. And the y-axis is just representing my cost, or the travel time, right? So if the travel time is higher, that means my solution is worse. If the travel time is lower, it's better. Okay, so it might not be the exact same shape, but let's say this is the shape of the solution space, okay, that I'm gonna get. So usually there are things called local minima, which are good things to be at. So a local minima is basically like you are at the lowest point of a certain dip around your solution space, and if you keep doing perturbations around it, you're probably going to get stuck there because this is the best you can do. But that's good. Most of the heuristics return solutions that are usually close to local minimum. There is something called the global minimum as well, which is the most optimal solution. But more likely than not, any heuristic will not end up at that global minimum because it's very hard to actually prove that this is the global minimum. We cannot, remember, when we did the exhaustive search of the solution in the first lecture for milestone 4, we saw that to do this exhaustive search, it would take more than the age of the universe, right? So we cannot prove that this is the global solution. And even if a certain heuristic finds it, it will say that this is the best I can do, but I cannot prove that it's better. It's the best, sorry. Okay, so let's look at the heuristics that we can do. Now, let's say that I just want to pick any random order of the deliveries. Where do you think this will fall off? Will it fall off like very low in the search solution space, or somewhere in the middle, or somewhere high up there? Like I'm just checking, like, getting a random delivery order. I'm not even doing any heuristic, just a random delivery order. Yes, Alex?
Maybe I spread it out.
What do you mean spread out?
Like spread out along the solution axis?
Yes, but what's the probability that you will end up with a good solution?
I don't know.
It's probably low. So you'll probably, most likely than not, you will end up at like solutions that are high enough in the search space. So they are not good solutions. Why? Because these are random solutions, and they are not based on any educated guess or any intuition, right? So the solution might be very poor, many more, usually in any optimization problem, there are many more bad solutions than good in the search space. And that's known about any algorithm. Like with anything you can do, you'll probably end up with a worse solution if you choose to do things randomly, okay? Now, let's do multi-start. So remember that we said that you can try the same thing that you're doing from multiple different points and choose the best one out of these, and this is called multi-start. So let's say we're sticking with the random order, we're just choosing a random order, but we're changing the seed, for example, for the random number generator and saying that I'm gonna choose a different random order as well and compare them, right? So yeah, it might change where you are located in the search space, but you are still at the high points in that solution space, right? If you choose the best one of them, okay, that's a better one than what you, if you just choose one that is completely random, right? So we chose the best one out of these four. It's still a bit better, but it's still not very good, right? The space is very big, and most likely we are at a bad solution point. Okay, let's look at the greedy algorithm. So what does the greedy algorithm tell us? The greedy says that the next decision that I'm gonna make, or the next dimension that I'm gonna move into, is the one that is going to give me the best travel time right now, right? So we start at a certain position, and greedy usually brings us somewhere around the middle, right? Let's say we started here, and greedy will bring us somewhere in, like a good enough solution. So it's not the best, it's a good enough solution. But it's definitely much better than random. Okay, so what about iterative improvements? We defined all of these perturbation operators that we talked about. Do they actually benefit us or not? Remember, in iterative improvement, you're doing some perturbation, see if the solution is legal, and if it has a better travel time, I'm gonna take it and continue iterating, improving on it. So let's say I start with a greedy solution, and I try to improve on it. So what iterative improvement, some solutions will be worse, and I'm gonna throw them away, right? Some solutions will be better, okay? If it's better, I'm gonna take it. So if the blue dot here is a better solution, I'm gonna take it and continue moving in that direction. So I try one, I try another one, and I try the third one, and it might bring me to a local minimum, which is good. Now, this is the best solution that I can find with this certain iterative improvement, right? So if I just swap the deliveries of two deliveries, or just change the position of one of the delivery, I might end up at a better solution. And this is why iterative improvements work better than greedy, right? So now we are at a local minimum. It might not be still a very good solution, but it's definitely much better than where the greedy left us, right? We can combine this iterative improvements with multi-start. So I can start from multiple different solutions by changing the way I do the greedy algorithm somehow, okay? And each one of them, I apply the iterative improvements on it. So what will this give me? So one of them will continue where I was, right? Another solution will start at a different place in the solution space and will improve on it and gets to a different local minima. This one also gets to a different local minima. And then I choose the best one out of these four. So in this case, the best one is this, right? So definitely multi-start can help me get out of local minima if I'm at a different spot of my solution space. Okay. But in general, this is the best what you can do in if you're sticking with those, for example, perturbation operators, right? However, if you come up with your own perturbation operator, or if you choose, for example, 2-op, because it severely changes the order of the delivery and it significantly disrupts how the solution is, it might get you to a different spot in the solution space and get you out of those local minimas, okay? So, for example, let's say that you are stuck here. Whatever improvements you're gonna do, you're gonna find a worse solution, and you're not able to get out of, right? So if we use more powerful local permutations or perturbations, we might end up moving us somewhere else, okay? This is slightly better than the local minimum, and we're gonna take it, and now we can apply different permutations again, and it will get us to a better solution, right? So the more complicated the perturbation operator is, the larger the part of the space it can explore, and probably the better solution it will find. However, you will not be able to try as many perturbations because usually these complicated perturbation operators are slower than the quick ones, which like swapping or like moving. So remember, like in 2-opt, for example, there are like 1 million combination. In 3-opt, there are like, I think 60 or 100 million combinations. So and it's slower. And you will end up probably with more illegal solutions that you have to legalize or throw away. So it's true that they can get you out of local minima. The problem is that you probably cannot try as many perturbations. Okay, so you need a balance between the perturbation operators that you choose. That's why we suggest that you can choose, like in this case, we define 3 different perturbation operators, and I'm telling you, like, you can choose one of them depending on how the solutions look like. If you find yourself stuck in a local minima, like you can opt to do like a 2-opt perturbation and trying to get out of there. If you're seeing that you keep improving from the previous iterations, you can stick with the quick ones that you can quickly legalize and evaluate. Okay. Another big heuristic that we haven't talked about, it's called hill climbing. So let's say that you are stuck in this local minima, and even 2-opt is not be able to get you out of, right? Like, it can happen. What hill climbing tells you is that I'm going to accept a worse solution in the hope that it gets me out of this local minima in the future, okay? So let's say I'm at this yellow dot, and my next evaluation is this red dot, and it turns out it's slow. It's worse. So let's say that I'm gonna take it. Like I'm gonna try and see if it gets me out of the local minima later on. At the same time, while I'm taking it, I'm gonna save somewhere the best solution that I found so far, because if I end up running out of CPU time and I'm like far away in the solution space, I want a way to go back to the best solution I found so I can return it quickly to the user. Remember, you have 50 seconds in this milestone to find a good solution. So hill climbing tells you that take the red one, then take a worse solution. Now notice here, by disrupting this worst solution, we found a solution that is better than it. Let's take it and see where it gets us. Now it's getting us a better solution than even the one we started with, and we continue doing so until we reach. Now we are lucky here that we got to the global minimum. It's not guaranteed that we're gonna get the global minimum, but it's basically telling us hill climbing can work if you do it smartly, and it can get you out of local minimum if you're stuck in one. Does that make sense? Any questions on this? You have a question?
Wait, I just have a question for the solution space. How do you know that it's linear?
How do you know it's what?
How do you know that the solution space is linear?
Linear? It's definitely not linear. Like the solution is definitely not linear. You can see the curve here.
I mean, like, how is it like continuous?
Oh, how it's continuous? Yeah. No, this is just a projection. Like this is just for my imagination. Again, the solution space is 200 dimensional. I cannot draw the shape of it, right? So you're probably jumping from different parts in the solution space. Even if you think it in 3D, you're probably jumping in different parts of this 3D space, right? So we cannot imagine it, and this is just for illustration purposes. So it might not be continuous, right?
But if it's not continuous, I guess won't the concept of like local minimas and stuff not?
Local minima in terms of the cost that I'm evaluating at, right? So the cost is, what is the cost? It's a travel time, and the travel time is a real number, right? So a local minima is just like you're stuck in, you tried one solution, okay? It turned out it's worse than the one that you have right now. You tried a different solution, it's still worse. That's the concept of local minima. Local minima is that you're stuck at a point that no matter how many perturbations you're doing, you're not able to find a better one, okay? So usually they translate to such a thing in the solution space. Now again, this is a travel time, so it might be continuous. It actually is continuous, it's a real number, right? But we don't know the shape of this solution, so it might, if you are able to find a better solution, so usually you are like at a slant, right? If you're not if you can't find a better solution, then usually you are like at a lower tip of a curve. Does that make sense? Yeah.
Is there
Yes, so that's a good question. So the next algorithm I'm going to talk about, it's a popular algorithm called simulated annealing, and it basically implements this hill climbing mechanism. And we're going to talk about how to implement it. Yeah. Okay, so one thing to watch about when doing hill climbing is that you have to watch the CPU time. That's why we say that save the best solution that you found, because if you keep doing hill climbing, you might be unlucky in finding actually a better solution. And if you run out of CPU time, let's say you are close to the 50-second and you have to return something, you don't want to return a worse solution. So you revert back to the best solution that you found and just return it. So you have to be careful with your CPU time here. Okay. So this is the fourth heuristic we talk about. Again, it's called hill climbing. And it gets us out of a rut or like a local minima by changing something even if it looks like a bad idea. So hill climbing, we can apply it to our solution by change the delivery order. Even if it increases the travel time, try to take it. Again, good idea to save the best solution that you found so far. Then we try local perturbation about that, around that new solution, any of the perturbation operations that we've implemented. Maybe you find something better, maybe not. Keep going. If not, eventually go back to your safe solution. And this way, hill climbing lets you explore more the solution space. It can move you around, you remember that curve? It can move you to a different spot in that curve. Okay, and that brings us to simulated annealing. So there is something called meta-heuristic. A meta-heuristic it's a general idea that is less specific than an exact algorithm. So it's not an exact algorithm, but it can apply to any problem. So it basically is a procedure that you can turn into an algorithm for any different kind of problem or different sorts of problems that you are working on. Okay? One of these popular meta-heuristics is called simulated annealing. And it's inspired from the annealing of metals. Probably haven't tried this at home. I don't recommend trying this at home. But like when they create metals of different shapes, they usually cool the metal slowly. Why is that? Because when the metal is very hot, the atoms are moving really fast and they are in an excited state. They are not like moving in random directions. If you take that metal, hot metal, and place it in water, it will cool quickly, and that's called quenching. And the atoms will freeze in the shape that they were at. So you'll usually get a less quality metal and of a very random shape. When you cool it slowly, and that's called annealing, the atoms gradually move to a lower energy state, and eventually the resulting metal will be much stronger because now the atoms are, once they get to a lower state, they get close to each other, and the bond between them is much stronger. And that's the idea of simulated annealing. So this algorithm is inspired of such phenomena. So the optimization, it's an optimization from framework that mimics annealing. We start with a poor initial solution, or we can start with a greedy solution, which is good enough, right? We can start with any solution, even a random order. And we say that we're going to start at a high temperature, okay? Now, we don't know what this temperature is. Like, let's say we define some high temperature. We perturb the solution and move the atoms. Most perturbations will be accepted when the temperature is high, because the atoms move at a very high speed and in very random directions when the temperature is high. We're going to say we're going to do the same thing. At the very high temperature, we're going to accept any solution, right? With a high probability, even if it's a worse solution, I'm going to take that solution and accept it. And that's part of the hill climbing, okay? When the temperature reduces, now the atoms are in a better state, a lower energy state. I'm going to take only the good ones. So that by good ones, I mean the ones that reduce my overall energy or reduce my overall cost, which I will define, which is in this case, most probably going to be the travel time. So once the temperature approaches zero, only the best solution, only the solutions that make me better, I'm going to take these. I'm not going to do hill climbing anymore because that's the best I can do, I think. Okay, so let's look at the pseudocode of the algorithm. Again, I can start with some initial solution. This solution can be random order, or it can be a greedy solution, which is usually good to start from a good enough solution, like a greedy solution. And then I define some cost function, like I will create a function that I call to evaluate my solution. In this case, it can be the travel time. But you can add to it, the good thing about simulated annealing, it can work with any nonlinear cost function. So you can add to it another metric that you feel like you want to penalize solution for. For example, if solutions that are more, if some perturbations get you more illegal, I want to penalize somehow in my cost function, so you can add that to the cost function somehow. In this case, let's say that we're gonna stick with only the travel time. We start with some high temperature T, and then in a while loop, we say that while the solution keeps changing, or like while I haven't arrived to my 50-second constraint, for example, I'm gonna keep trying doing things. Inside the while loop, I'm gonna create a for loop that will do like many iterations. These many iterations can be permutations, sorry. They can be 10, they can be 100. Again, we will talk about tuning these parameters. So in each of these iterations, I'm gonna say that take S new, which is a perturbation, some perturbation of S. What is this perturbation? Can be one of the operators that we talked about. It can be some new operator that you come up with, okay? And then I'm gonna define C new to be the cost of this new perturbation by calling the function to evaluate. And I will calculate delta C. Delta C in this case is the difference between the new cost and the cost that I started with, or the cost of my current solution. Okay? If this solution is less, if this delta C is less than 0, okay, that means it's a better solution. I'm just gonna update it and take that new cost. Now, so far, there is no hill climbing. Like, this is just an iterative improvement, similar to the iterative improvements we've been doing, right? Take the better solution. To do hill climbing, we will add this red term, okay? We are saying that with some chance of, with some probability, we are going to accept solutions that are even worse. And this is represented by this formula. So I'm gonna pick up a random number between 0 and 1, and say if that random number is less than this exponential, I'm gonna talk about it in a bit, then I'm gonna accept the solution. Okay, so if the solution, if the delta C is negative, then I'm just gonna stick with this first term and I'm gonna take the solution, right? If the delta C is positive, there are several cases. Now, if delta C is positive and it is it's very high, then this is probably going to be, and let's say that the temperature is really low, so this is probably going to approach 0, okay? If it approaches 0, so no matter what random number I choose, I'll probably reject it. Now, if the temperature is still high, like high enough, and even if delta C is high, then this is probably this term is probably going to approach 1, and whatever random number generated I get, it's probably gonna accept the solution. So at high temperatures, and I will probably accept solutions even if they are worse. At low temperatures, only probably the good solutions I'm going to accept them based on this random number. Does that make sense? Yeah, cool. Okay, now I end my for loop. After I do some number of perturbations, in order to converge, I need to reduce my temperature. Remember, if the temperature stays high, I will keep accepting new accepting solutions even if they are worse. But we want to move towards a direction where only the good solution will be accepted later on. And that's why we will call this function called the reduced temperature. And again, we don't know how to reduce it. It's probably empirical. Okay, so let's look at just an example quickly here. So this illustrates like the different possibilities that would end up. If the delta C is negative, no matter what the temperature is, with 100% probability, I'm gonna accept it, okay? Let's say my delta C is positive 30 seconds, so my solution is worse, 30 seconds worse, which is usually not that bad. Like when we talk about the deliveries, we're talking about like hours or minutes, right? So 30 seconds is probably nothing. And let's say my temperature right now is at 30. If you evaluate this, I have a 37% chance of accepting this solution. Let's say the delta C is 30 and my temperature is much lower, okay? It's at 5, it's at 10 right now. So my probability decreases to accept decreases to 5%. If you decrease the temperature further but fix the delta C, your chance of accepting the solution will be much lower as well. It's gonna be at 0.005%. So you probably not accept worse solutions in this case. Now, if your delta C, if you keep the temperature at 3, but the delta C is even smaller, even at this low temperature, you might end up accepting it because the acceptance rate increases to 37%. So that's the good thing about simulated annealing. It looks at both the temperature and how far is the new cost is. If the cost changed slightly in the worst direction, it still might be a good idea to accept it because, again, it's like a difference of 3 seconds here. If the costs change significantly, then I will only accept it if the temperature is really high because at low temperatures, it's probably I converge to a very good solution and I probably won't find a better solution anymore. Make sense? Okay, now the problem with simulated annealing, as you can see, is that it needs a lot of tuning. There are several parameters that you need to tune. There are several things that are still uncertain, and usually we define these based on empirical experimental setup, right? So we run some simulations over and over again and see what works for our problem. So one of these things that we need to tune is, what is our initial solution? Do we just start with a random one or like a smarter one? Usually a smarter solution, like a greedy starting from a greedy solution is better because right now you are in the middle of the solution space instead of being at the top. The second thing that we need to tune is the cost. Again, we can define any cost function. Is it just going to be the travel time, or like are we going to add an extra metric that will penalize something else? That's also up to the developer of the algorithm. They can do a lot of experiments and see what works best. Temperature. So far we've said that we're going to define this temperature to be really high. But how high? How high is that? Like, is it like 1,000, 1 million, 100 million? We don't know. Again, all of these are, we call them hyperparameters of the algorithm that will need to be tuned somehow through experiments. Okay. The last thing that you probably need to tune is also how to reduce the temperature. If you reduce it very quickly, like in quenching, for example, of metals, you will probably end up with not a very good solution because the atoms froze quickly, right? So you will need to slowly decrease that temperature so that you give your algorithm the chance of accepting worst solution in the hope of getting out of your local minimum. Make sense? Okay. Also the perturbations, like we defined only 3 perturbation operators. You can come up with your own and see what works best. In my PhD, for example, I implemented the simulated annealing algorithm for a different kind of problem, which was like how to plan a medical therapy, right? Like I want to place some sources that optimizes my treatment. And I use simulated annealing to choose the placement of those sources. And I did, on top of the perturbations, different perturbations or different moves that I decided I want to make, throughout the algorithm, I used a reinforcement learning agent that basically looked at the history of what were the most accepted solutions previously, and I'm going to increase the priority of choosing those type of moves later on. So people do lots of different kinds of algorithms or like educated guesses on these in order to see what works best throughout the algorithm and adapt accordingly. Okay. Yeah, and same thing you can do for the temperature. Like you can see if the solution is getting much better with hill climbing, probably I won't decrease the temperature as quickly. If the solution is not improving anymore, I only want to decrease, I only want to choose solutions that are better, then I'm just going to decrease it quickly. Okay, so this is a bit about the meta-heuristics. There are other courses that will actually tell you, introduce you to different other meta-heuristics and optimal solutions of different algorithms. So in ECE345, which you should take next year, I really recommend this. You won't code in that course, but you will go into a lot of proofs and complexity analysis to prove that algorithms will return an optimal solution to you or not. So for example, Dijkstra and A-star should return an optimal solution to you if the turn penalty, for example, is 0. And in this course, you can prove that it's the case. Yes?
I have a question about the previous slide.
Yes.
Well, 2 things. First off, when you talked about the reducing the temperature, what were you seeing as the logic of if you should increase, like how steeply you decrease it or not?
Yeah. So remember, like we are mimicking the annealing of atoms, like how you anneal metal, how you change the shape of a metal. You start with, you heat it up, you start at a very high temperature, and slowly decrease it. Why do we slowly decrease it? Because as you slowly decrease it, the atoms start to cool down slowly, and the atoms will go into a lower energy state, but they will be much stronger because they will like condense around each other in a way that are very well connected. If you take that metal and put it in the water, for example, and decrease it quickly, the atom will freeze immediately in the way, in whatever shape they were in, okay? So they were in a very high state, they were in random directions, they will freeze wherever position they were in. Now, that usually results in a lower quality metal. Same thing in the algorithm. If you decrease your temperature really quickly, that means you're saying that I don't want to accept any worse solutions anymore. I don't want to do hill climbing, and I'm going to stick with my solution right now. More likely than not, you're not going to get out of the local minima because you can't find a better solution if you are stuck in that position, right? If you stay at a high temperature and just slowly decrease it, you are saying that I'm going to slowly decrease my temperature, but at the same time, I'm not going to reject worse solutions yet, right? I will still accept those solutions in the hope of getting to a better solution later on. Does that make sense?
Yeah, it does. The only thing is, what I was thinking is if you're doing several perturbations, like around a point, won't you have like a behavior where it's just going to start going up and start going down and just still stay around the same area?
Yeah, you can end up at that situation, or you can end up, as you saw, that you get the worst solution, get another worse solution with a certain probability. That's the beauty of this term, right? Even if you keep going up and down, at some point you'll probably still keep going up because you just accept it by chance. And that will only be possible if you're still at a high temperature. If you're at a low temperature, you're probably not going to accept this anymore and try to find something worse, which you're not better.
The random probability would not be that likely, so you're probably not.
Yes. Yeah. This term would be close to zero if your temperature is low, right? Yeah. Okay. So other grad courses that are really good to learn, I took one of them in my grad school, and they will introduce you to different meta heuristics and different computationally hard problems. One of them is this ECE297, which is taught by Professor Jason Anderson, and it will introduce you to like different computationally hard problems in computer-aided designs and integrated circuits, and and we actually use simulated annealing on one of those milestones. Another course is called Bio-Inspired Algorithm for Smart Mobility. It introduces you to different problems similar to like the traveling courier problem, something called the transportation problem, how to optimize traffic in a city, how to optimize building cities, etc. They introduce you to different kind of meta-heuristic called genetic algorithms. One of the algorithms is inspired by how ants move in colonies, and it's called ant colony optimization. I'm not going to go into the details, but yeah, there are different kinds of algorithms other than simulated annealing that might be beneficial and good to learn. Okay, so I quickly want to talk about how to manage your time limit in your milestone. Okay, so remember that you have 50 seconds in order to find a solution that is good enough for your to return, right? And we introduced different algorithms and different heuristics to go with, like multi-start, iterative improvements, that you can keep looking and even simulate annealing until you find a better solution. But with 50 seconds, you will need to constrain yourself on when to return from your algorithm. You can't keep running things, right? And we do this by checking the time in every iteration and see how far are we from the 50 seconds, okay? Since we are almost out of time, I'm going to go over this quickly. We use this through the chrono library to measure the wall clock time or the current time that I'm at. Okay, so I don't want magic numbers in the code, so I define at the top my time limit is going